And so we're already start really looking at solving equations, which is the bulk of what we're going to do for logs, especially in the bigger point problems, is solving equations, whether they're exponential equations that we solve using logs or log equations that we're going to solve through exponentiation. Okay, so the first set we're going to look at are the exponential equations. And so if I have something like, say, 5 to the x is equal to, I don't know, 17. What we're going to do is we're going to round our answers to thousandths, if appropriate, and it probably will be. Okay, so for this entire exercise, we're just going to round all of our answers to thousandths. And so I have an exponential, and again, nothing is slapping me in the face here. I can't really write 17 as a power of 5, which means now I'm going to go to my powers of 10, which is my logs. Okay, so when I do that, though, I'm going to take the log of both sides, and so that's the step. So you're going to take the log of both sides, applying your rules. And what I will end up with then, because this is an exponent, the exponent comes down as the multiplier on the log of the base, which is 5, and that'll be equal to the log of 17 on the other side. Now you can see how easy this is going to be now, okay, because all I have to do is to find x, divide the log of 17 by the log of 5. And when I do that, I don't have a calculator on me. This might be a good chance for you to pause the video and go grab a calculator. That way you can do the calculations at the same time I'm doing them, just to verify and ensure that you're actually entering this correctly into the calculator. So I'm going to go get my calculator, you go get your calculator, and then we can resume this. So I'm going to pause now. Okay, so when I punch into the calculator the log of 17 divided by the log of 5, and keep in mind that the log gives you an automatic left, so you have to make sure you close it off before you hit the division. Okay, otherwise you're going to end up with the wrong answer. X turns out to be 1.760 to the nearest thousandth, which is what we talked about up here. We're going to round these answers to thousandths, unless told otherwise. Okay, let's go to the next question. It doesn't matter how gross and complicated these bases get, irrelevant. The fact that there's no easy common base to turn these into says I'm going to use log base 10, which means use my calculator, which is fine. And so when I apply the rule, which is take the log of both sides, because remember, it's an exponential. We solve exponentials through logs. Take the log of both sides. Whatever you do to the left, you have to do to the right. And when you do that, once again, this exponent comes down as the multiplier on the log of 4.3, and that will be equal to the log of 9.2. So when I do this, x will be equal to the log of 9.2 divided by the log of 4.3. And rounding to thousandths, I get x equals 1.521. Rounded appropriately to thousandths. Hopefully you got that also. Here's yet another example. Probably a little bit more typical with our exponentials, because this would be more in the form of a times b to the x equals some number. So when we start getting into the application questions, this is more in line with what you're going to see. Now what I will tell you is, yes, I can take the log of both sides as is right here, but this is product, which means if it's a product, I would have to take the log of 3 plus x times the log of 4.5 equals log of 10. I would rather wait and do the logs once this has been isolated. Okay, so what I'm going to do is I'm going to put this base with its exponent in blue to show you that that is the power, which means this piece should go. And because that's product, I'm going to divide both sides. So once again, I'm going to isolate my power. That's not something new. We've been doing that right along. Isolate the base with the exponent before you decide what you're going to do next. So if I divide both sides by 3, which is what I want to do, okay, I will end up with 4.5 to the x equals. Now, 10 divided by 3, repeating decimal. I don't want a repeating decimal. Mixed number, 3 1/3, I don't want a mixed number either. I'm going to just leave it 10/3 because it is not pretty. Now when I take the log of both sides, again, my x comes down as the multiplier on the log of 4.5, and that will be equal to the log of 10/3. Now you could do the log of 10 minus the log of 3, not necessary. Your calculator can handle that division. Very user-friendly, those calculators. Okay, back when we had to use the charts, like I showed you in class, we had to do the log of 10 minus the log of 3. But now you can just do the log of 10/3. Okay, so again, x would be equal to the log of whatever 10/3 is, divided by the log of 4.5, and it doesn't matter if it's fractional or decimal, as long as it's a terminating decimal, you can go ahead and do that. If it's not a terminating decimal, leave it in fraction form. Okay? It doesn't even have to be reduced fraction form. That's the other beautiful thing. When you divide that, x will turn out to be, okay, x equals, drum roll please, go ahead and pause and do the calculation, make sure that you're doing it right, and then when you come back, the answer will be there. I got 0.800 because the next digit's 4, so I would leave it as a 00. Hopefully you got the same answer. If you didn't, make sure again that you're putting in just the way you see it. So when you hit the log and it gives you the left parenthesis, it's just 10 divided by 3, close it out, then hit the division. Okay, make sure you always close out that parenthesis to end the log. So here's a typical application problem. It's a compound interest problem. If we take $5,000 at 4.5%, compounded monthly, how long to the nearest year before the money doubles? That should be a question, right? So let's think about our formula. Our formula says the amount in the account is going to be equal to the principal, which is the initial value invested, $5,000 in this case, times 1 plus the rate divided by the number of times compounded, raised to the n times t. Now what we're actually looking for here is t. How many years before the money doubles? Doubles means 10,000. So what I'm looking for is the $5,000 to turn into $10,000. This 10,000 is what's going to come in here for A, the amount in the account, okay? So I'm going to start filling in my values. 10,000 is going to be equal to the original amount of 5,000 times 1 plus, my rate is 0.045 divided by 12, because that's my n, raised to the 12 times t. Okay, so the idea is I am looking for t. That's my exponential. In all the problems we've done up until now, I've known t, and I've been looking for the amount. So on these problems, typically, you're either going to be finding the amount if you know t, or you're going to be finding the year if you know the amount. So you'll either know the answer, or you'll be looking for the answer. You'll be looking for the time, or you'll be looking for the answer. So when I look at this now, my base is, here, this whole thing. And here's my exponent. This leading coefficient of 5,000 has to go. I'm going to divide both sides by that initial amount. And when I do that, when I divide the 10,000 by 5,000, I get 2. Okay? And that makes sense because I'm doubling it. So when I divide this whole thing by 5,000, this is gone. What I end up with is 2 equals. Okay? And then I have this rate, which is 1 plus 0.045 divided by 12. I am not going to change that into a decimal because I don't know what that decimal looks like. and that's raised to the 12 times t. At this point, I take the log of both sides. So it's going to be the log of 2 will be equal to this piece here, 12 times t, that's my exponent, times the log of the 1 plus 0.045 divided by 12. Now, this is what I'm trying to isolate right here. Okay, which means I'm going to divide out the 12, and I'm going to divide out the log. I'm going to do it one piece at a time. So the first thing I'm going to do is divide both sides by the log of the 1 plus 0.045 divided by 12. Okay, so I'm going to do that here. 1 plus 0.045 divided by 12. And then on this side also, the log of the 1 plus 0.045 divided by 12. I don't typically show this step, but because it's your notes, I'm showing you where it's going. So this and this go away. And then I'm going to use my calculator for this piece. And again, punch it in the way you see it, but don't forget your parentheses here. So I'm going to go to the next page. You'll see your answer. Okay, so I just transferred that to a new stage. When you take the log of 2, whoops, right here, and divide it by the log of 1 plus the 0.045 divided by 12, you get 185.1856055. That's what the calculator says. And of course, that's equal to 12t. So now if you divide both sides by 12, which is the next step, divide both sides by 12, your answer, t, turns out to be approximately 15.43. Now the problem originally stated to round it to the nearest year. So I would report 15 years by my rounding instruction. Okay? So again, you got to pay attention to the rounding because there's many, many, many points lost for incorrect rounding. Okay, very good. So this is the essentially what's going on with these exponential equations. And so tomorrow we'll look at log equations and solving those, wrap it all up and put it all back together. Okay, see you tomorrow.